Alright, you are welcome once again to our third lecture in our structures and functions of biomolecules. Alright, so today we are going to discuss a subtopic in biochemistry called stereobiochemistry. Alright, so stereobiochemistry, when you say stereobiochemistry, is how our biological systems in our body react. Okay, so how they react to molecules when we take them inside our body. For example, when we take drugs inside our body, how this system reacts to those drugs and how the enzymes in our body react to those drugs. Okay, so it deals with specificity. All right, so they are all specific in nature due to stereochemistry. Okay, so we are going to discuss stereobiochemistry. Okay, and when we say stereobiochemistry, is just a branch of chemistry that deals with stereoisomers, all right, conformation and all those stuff. So we are going to talk about them, and after that we'll talk about chiral molecules. Okay, so we are going to talk about chiral synthesis. So what are chiral synthesis? And we will identify all the chiral synthesis and the chiral carbons, and we give examples so that in case you meet some in the exams or in any test, you'll be able to identify them. And after that, we talk about specific rotation. Okay, so we are going to talk about observed angle of rotation, the concentration and the length, how they are able to make rotate a plane polarized light. So we are going to talk about specific rotation as well, and we will do some basics calculation inside so that you will be familiar with such calculations. And after that, we will talk about enantiomers. All right, we will talk about enantiomers, diastereomers, and meso compounds. So we will talk about what they are, and we'll give examples and all those stuff. And after that, we will talk about stereobiochemistry. So we will discuss how these biological systems respond to active enantiomers. Okay, so as I said earlier, all the enzymes in our body are stereospecific. So okay, so they are optically active and they react to a specific enantiomer of maybe drugs so that it can effectively cure any disease that's intended in the body. All right, so without wasting my time, let's start with stereochemistry. So when we say stereochemistry, okay, so stereochemistry, it is a branch of chemistry concerned with the three-dimensional arrangement of atoms and molecules and the effects of this chemical reaction. Okay, so when we talk about stereochemistry, it just deals with stereoisomers, and they represent molecules in a three-dimensional view. Okay, so all these molecules over here, they are represented in 3D views. All right, so three-dimensional views. Okay, so that's stereochemistry. And we say stereoisomers, they have identical molecular formula. So they are atoms or molecules with the same formula, okay, with atoms bonded in the same sequence, but they differ in the way they are arranged in space. All right, so when we say stereoisomers, so this is the branch of stereochemistry, that's stereoisomers. All right, so within this stereoisomers, we have configurational isomers and we have conformational isomers. All right, so they have the same molecular formula. All right, but their arrangement in space differ. Okay, so let's take example. We have this figure here, we have this figure here. They all have the same molecular formula, but see, the arrangements in space differ from each other. Okay, so that's basically what's meant by stereoisomers. So let's talk into details of these stereoisomers. So stereoisomers is a branch of chemistry that deals with 3D views of molecules. Okay, so under stereoisomers, we have configurational isomers and we have conformational isomers. Okay, so this conformational isomers is just the interconvertibility between molecules around a single bond. Okay, so when we check this molecule, we have only single bond here we have 1, 2, 3, 4. So it's a 4 carbon atom. All right, so 1, 2, 3, 4. So it's a 4 carbon atom, and all the bonds involved are single bonds. Okay, so it's conformational isomers. And when we say configurational isomers, these are around a double bond, and some are mirror images too. Okay, so we under the configurational isomerism we have geometric. So geometric is interconvertibility between double bonds. Okay, so we have isomers, and these isomers there are double bonds involved. Okay, and we have optical under configurational too, and under optical too we have enantiomers and we have diastereomers. Okay, so when we say enantiomers, they are molecules, they are mirror images of each other. All right, so we'll talk about it details in few minutes time. So these are mirror images of each other. So let's draw. When we draw a straight line here, you can see that where the chlorine is the same position as where the chlorine is in this second molecule here. So it's just a mirror images of each other. We talk about chiral centers, and you get to know more about enantiomers. And under the optical too, we have diastereomers. These diastereomers, they are not mirror images of each other, although they have chiral centers, but they are not mirror images, and they differ from each other at just a 1 carbon atom. So one chiral center is just the difference between stereoisomers. Okay, so this is stereochemistry, and that's what stereoisomers are. Okay, so let's talk about chiral molecules. Okay, so when we say chiral molecules, so chiral molecules is just an asymmetric molecule that's optically active. Okay, so let's talk about this asymmetric molecule. When we say something is asymmetric, that means it's not having any plane of division. Okay, so it's aplanar. Okay, so it's not having any plane of division. All right, so for example, when we take this compound, for instance, we have CH3 here, we have chlorine here, we have bromine, we have a hydrogen and 1 carbon atom here. So this carbon atom, when we check all the bonds around, it's not having any similar bonds. Okay, so this hydrogen is different from this methyl group, and this methyl group is different from this chlorine, and this chlorine too is different from this bromine. So it's not having any symmetry. So you can't divide this compound into 2, 3, 4, or any else. All right, so it's asymmetric molecule that are optically active, and they rotate plane polarized light. Okay, so all these here are chiral molecules. This is chiral, this is achiral. Because this is achiral, that means we have a plane of division. Okay, the reason why we have a plane of division here is we have a CH3 here, we have a bromine, we have hydrogen here. So there is hydrogen and hydrogen, so we can divide this in this plane, and we can get hydrogen on one half and another hydrogen on the other half. So it's symmetrical, so it's having a plane of division. Okay, so let's talk about chiral centers. When we say a chiral center, it means a tetrahedral carbon atom attached to 4 different group of atoms. Okay, so a chiral center is a carbon atom. So let's take this compound, for instance. We have a carbon atom here, and this carbon atom is tetrahedral. Why is it tetrahedral? Because it's surrounded by 4 different group of atoms. So that comes the name tetrahedral. So 4 different group of atoms, and this carbon here is chiral because it is not symmetrical. That means it's asymmetry because we have different group of atoms around this carbon bond. So it's different. So hydrogen is different, this is different, this is different, this is different. So we can represent them by A, B, C, D. And A is different from B, B is different from C, C is different from D, and D is different from A. So this compound can be termed as a chiral molecule. And the carbon here can also be termed as a chiral center or a chiral carbon. Why? Because it has 4 different atoms bonded to the carbon. Okay. Alright, so likewise we have achiral. So achiral does not have 4 different atoms or groups bonded to the carbon. This is because it's having 2 hydrogens, and these hydrogens too are similar, so they can't be different. Okay, so we have another chiral compound here, and when you check this compound, we have a metal group, we have an ethyl group, and we have a propyl group here and a hydrogen. So they are all different together. So we have 4 different groups bonded to the carbon, so it can be termed as a chiral molecule and a chiral carbon too. So when we take this compound too, for instance, it has 3 atoms bonded to the carbon. So we have this bond, this double bond bonded to the oxygen. We have a bond, single bonded to methyl group, and a single bonded hydrogen. So we have only 3 groups of atoms bonded to this carbon. And from the definition of a chiral center, is a tetrahedral carbon atom, and this is trigonal, so it can't be a chiral center. All right, so this is what chiral molecules are, and when we see chiral center, this is what it means. All right, so you can pause the video and you can go through so that you'll be familiar with the terms. Okay, so we have specific rotation. So when we talk about specific rotation, is the degree of rotation that is recorded in degrees. It's an angle of rotation, and it is recorded in degrees, all right, of the plane of polarization of a ray of monochromatic light. When we say a monochromatic light, it's just a light with only one source, all right, a light with only one direction. It's just from one source, so it's a monochromatic light that passes through a tube of 1 decimeter long, okay, 1 dm, containing the substance in a solution at a concentration of 1 gram per millimeter in a polarimeter. All right, so this whole thing summarizes to give this simple equation. So specific rotation is this is the specific rotation, that's alpha here, and this is the observed angle of rotation. Okay, this is the observed angle of rotation that is represented by alpha naught. You can represent it by alpha naught, and this C here is concentration, and this concentration is recorded in gram per mil. Okay, so in calculations they can give this to you as in, let's say, kilogram per meter or any conversion. So when you are given either cm cube, gram per cm cube, that means you have to convert it into gram per mil before you can use it in calculating what the specific rotation. If not, it's going to be wrong. Okay, and the L2 is the length of path, the path length, and it's also recorded in dm, that's 1 decimeter. Okay, and the changes 10 cm cube is equal to 1 decimeter. All right, so that's the conversion, and the alpha here is the observed rotation. That's the rotation observed for a specific sample. Okay, so this is optical activity. So that's how we measure optical activity of a solution or any solution. All right, and remember the concentration is in 1 gram per millimeter, so gram per mil, and the length is in 1 decimeter. All right, and the angle is measured in degrees. Okay, so take notes of those measurements and the units as well. Okay, so let's do some simple calculations involved in specific rotation. So a sample with a concentration of 0.3 gram per mil was placed in a cell with a length of 5 centimeter. The resulting rotation of the sodium D line was 1.52 degrees in the positive direction. What is the specific rotation? That is the alpha with sodium lamp, that's D lamp. Okay, so that's how it is represented. So how can we go about this question? So when you are given this question, for instance, what you have to do is to write down the parameters. Okay, so the parameters, we have concentration, that's in 0.3, and the unit is in gram per what ml. Okay, so as we talked earlier, the concentration is supposed to be in gram per ml in our previous video. Okay, so the concentration is in 1 gram per milliliter. All right. So after the concentration, it was placed in 5 centimeter length. And remember too, we talked about the length, and we said it's also recorded in dm, that's decimeter. So you have to convert this centimeter to what decimeter before you can use it in the calculation. All right. And the resulting rotation at the sodium D line was positive 1.52 degrees. Okay, so what's the specific rotation? So in solving this, you have to first convert the 5 centimeter to a decimeter, and this is the conversion is 10 centimeter is equal to 1 decimeter. Okay, so if 10 is equal to 1, then 5 will be equal to 0.5. Okay, so we just half of it. Okay, so after that, you can start and substitute it in the equation. All right, so we have the specific rotation here, and it's equal to the observed angle of rotation divided by our concentration times the length. And the observed angle of rotation in the question was 1.52 degrees in the positive direction. Okay, that's divided by 0.3 times 0.5, and it's going to give us plus 10.1. So the specific rotation is 10.1 in the positive direction. So this is how you can do some basic calculation in specific rotation. All right, so you can try more examples on it, and it will really help. Okay, so our next topic is enantiomers and diastereomers. So we are going to talk into details what are enantiomers and what are diastereomers. So let's start with enantiomers. So when we talk about enantiomers, they contain chiral centers. Okay, enantiomers contain chiral centers that are not superimposable, and they are mirror images of each other. Okay, so for you to get an enantiomer, one, we have to get a chiral center, and the molecule too, you have to get a mirror image of it. And the mirror images, they are not supposed to superimpose. Okay, so when you place one on each other, they are not supposed to fit. All right, so let's take this for instance. We have an enantiomer here. So enantiomer, they are stereoisomers that are mirror images of each other. So let's take glucose. All right, so this is the molecular formula for glucose represented in a Fisher projection. So this is a Fisher projection of glucose. All right, and this is the D-glucose and the L-glucose. That's the isomers of glucose with this enantiomer. So we have CHO, that's the aldehyde group, and we have hydroxy group here, hydroxy group. All right, okay, so let's check this compound. For instance, when we draw a straight line here, we can see that OH here is here, we have OH here too, we have hydrogen here, we have hydrogen here, we have OH here, we have OH, the same thing, we have OH here, we have OH here. Okay, so this is a mirror image of this one, and when you place this on this, that means the OH here is going to be here, and it's not superimposable. Okay, that means it's not going to fit. All right, so that's an enantiomer. Okay, that's an enantiomer for you. All right, so let's go back to diastereomers. When we talk about diastereomers, they contain chiral centers. Okay, and they are not superimposable, but they are not mirror images too. So for instance, this molecule here, it has a chiral center, and it's not superimposable, but it's not a mirror image of each other. So it can't be an enantiomer. So that means it's a diastereomer. So for instance, let's check here. We have one OH here, which was supposed to be at where the position of the hydrogen was if it was a mirror image. Okay, so since we have an OH here and we have a hydrogen here, it's not a mirror image. Okay, so it can't be an enantiomer. And one note that you have to take in order to identify a diastereomer was here. So diastereomers, they differ from each other in configuration at only one chiral center. Okay, at only one chiral center. So let's check this compound. We have an aldehyde group here, CHO. We have a hydrogen here. We have OH here. And this carbon that is attached to this is also a different group. So this is a chiral center. Okay, the second carbon is a chiral center. All right. And when we take the D-galactose, for example, we have a metal, the aldehyde group here. We have on the second carbon hydrogen OH, and also the third carbon is different group. So it's the second carbon here is also a chiral center. So they are chiral centers, but the position of the hydrogen and the hydroxyl group differ. So it's not a mirror image. So when you check all the other carbons from carbon 3 to carbon 6, they have the same position. Okay, so we have OH here, OH here, we have OH here, OH here. All right, so these are diastereomers. They differ from each other at only one chiral center. Okay, so that's diastereomers for you. Okay, so when we talk about anomers, they are in carbohydrates. So we'll talk about carbohydrates in our next lecture, and you get to understand what anomers are. They are just interconvertibility between two anomeric forms, the alpha and the beta form. So we'll talk about it in our next video that we are going to do. Okay, so this is also a meso compound. So let's talk about a meso compound. Okay, so when we talk about a meso compound, what's a meso compound? A meso compound is a non-optically active. Okay, so the underlying word here is not optically active. Okay, so a meso compound is a non-optically active member of a set of stereoisomers, at least with two chiral centers. Okay, so which is supposed to be of two optically active centers. That means it's having two chiral centers, at least two chiral centers. And this means that despite containing two or more stereogenic centers or chiral centers, the molecule is not chiral. Stereogenic center is the same as chiral center, so don't be confused. Okay, so a meso compound contains at least two chiral centers and is not optically active, because when we talk about optically active compound, it's not supposed to have a plane of division. So let's take this compound for instance. We have a chiral center here, we have a chiral center here, as the line shows over here. So this is a chiral center because it's bonded to 4 different group of atoms, and the carbon here is a tetrahedral carbon. This also is a tetrahedral carbon. But what we have to know that when we draw a line here, this is a mirror image of this. Okay, so it's having a plane of division, and when we superimpose this on this, it's going to be exactly as the same thing. So it's not optically active. All right, although it's having a chiral center, it's not optically active. So they can ask you in a multiple choice question that is all chiral molecules optically active? And the answer is no, because this is having chiral centers although, but it's not optically active. Okay. So this is a meso compound for you, and it's not optically active because it's having a plane of division. Although it's having chiral centers, but it's superimposable on each other. So that's a meso compound for you. Okay, sharp. Okay, so we are going to talk about our last slide, and we are going to talk about stereobiochemistry. Okay, so as I said in the beginning, biological systems, they only have one enantiomer that they are specific to it. So many compounds in the biological system have only one of the enantiomers, okay, that's optically active. So when we take for instance that D-glucose and the L-glucose that we were talking of, the system in our body responds to only D-glucose. It's a sugar. So when we talk about sugars, our body, okay, responds to the D-glucose. Okay, that's the sweetest one. So the body responds to D-glucose. So it's specific. Okay, so biomolecules, they are stereospecific. And the enzymes in our body too, they are optically active. So they are also stereospecific. Okay, so they have only one enantiomer that's optically active. And this happens because both the enzymes and the cell surface receptors, which metabolize the activities, are all what? Chiral. So they are all chiral molecules. So they are what? Specific to each other. So they react specifically. So the chiral receptor fits the arrangement of the substituent in only one enantiomer. Its mirror images does not what? Fit properly. Okay, so for instance, when we have a drug, let's say we have a specific drug, and every drug too is optically active, so it's supposed to have a mirror image. So we have a D and an L. Okay, so they are enantiomers, so we are going to have a D enantiomer and L enantiomer, but our body will respond to only one of that enantiomers. Okay, so the body will respond to only one type of enantiomer. So it's going to pick either the D or the L based on the one that's going to effectively cure the disease. All right. So note, for many drugs, only one of the enantiomer is biologically what? Active. Okay, so although they are optically active, but only one is biologically active because our body is going to respond to only one of the enantiomers. All right. So for example, we have this disease we call Parkinson's disease, and this disease is a disease of the brain that when you get this Parkinson's disease, you'll be suffering from shivering and all kind of stuff that you can't be able to reason well. So it's a very deadly disease, and for this Parkinson's disease, we have a drug called dopamine. All right, so dopamine is able to cure the Parkinson's disease, and this dopamine we have is an optically active because it's a drug. It's supposed to be optically active. So we have the L-dopa and we have the D-dopa. Okay, so the L-dopa is moderately effective in the treatment of Parkinson's disease, and dopamine, that's D-dopa, okay, is biologically inactive. So the body does not respond to D-dopa, but rather what? It responds to L-dopa. So that's how it's able to treat Parkinson's disease. Okay, and dopamine responsive dystonia, DRD, by stimulating the production of dopamine in the brain. So only the L-dopa is able to stimulate the dopamine in the brain so that it can effectively treat the Parkinson's disease. So that's stereospecificity for you. So biochemistry, we deals with stereospecificity. So enzymes and biomolecules and everything that's in biochemistry, they are all stereospecific. All right. So that's how come we are able to manufacture drugs, and the drugs are able to function well because our body is going to respond to only one specific enantiomer, and that enantiomer is going to help cure that disease. All right, so that's the end of today's slide. So in summary, today's slide it was about stereobiochemistry, and we talked about stereochemistry. We said they have stereoisomers, and we talked about specific rotation. We talked about enantiomers and diastereomers. We talked about a meso compound. All right, and finally we talked about stereobiochemistry. All right, so that's the end of the slide. And please don't forget to subscribe, like, comment, and share this video for us. Okay, so if you have any comment, you can just enter into the comment section and type any question or any suggestion that you have for us, and we will answer you immediately. Okay, so kindly subscribe to this channel. And this stereobiochemistry too is very, very important. All right, yeah, because the body needs specificity in order to function, because in case the body doesn't respond to the L-dopamine, unfortunately it responded to the D-dopa. That means it's not the body is not functioning well, and it's going to bring a misfortune, because it's going to produce something that's different from what the body needs, and that's going to be deadly. All right, so that's the end of the slide. And our next video, we are going to talk about carbohydrates. All right, so that's the next video for our structures and functions of biomolecules. Okay, so stay blessed, and as I said earlier, don't forget to like, comment, and subscribe to this channel for us. All right, thank you. Alright guys, welcome back to the structures and functions of biomolecule course. Today is our fourth lesson, and we are bringing to you carbohydrates. So we want to study carbohydrates, and before we can study carbohydrates, we have to know some basic terminologies before we can study carbohydrates into very details. Alright, so today we are going to study those terminologies one by one and know what each of them means, so that our next video will tackle carbohydrates, and it will be very easy for us to move at a faster pace. All right, so we are going to talk about key terminologies in the study of carbohydrates. Okay, all right, so learning objectives are going to be anomers. So we are going to talk about what anomers are. All right, so we're going to talk about EPIMERS, MUTAROTATION, penultimate carbon, glycosidic bonds, hemiacetal and acetal links, hemiketals and ketal bonds, HAWORTH projection, Fischer projection. Okay, so we are going to talk about all these things into details and tell what each of them are. So our last video, we talked about stereoisomerism, and we talked about enantiomers, we talked about their stereomers, meso compounds, and the rest. Okay, so in the study of carbohydrates, they all apply. All right, so we are continuing with these terms so that carbohydrates will be very easy for us. Okay, so in studying carbohydrates, we need to include stereoisomerism. Okay, we need to know optical activities, we need to know chiral centers, as we studied in the previous lesson. That's lesson 3. So if you've not studied lesson 3, you can just check in the description below, and you can find the link to lesson 3, so that you can go back and read and learn before you can able to acquaint yourself with this new topic. Okay, so we are going to talk about anomers, EPIMERS, MUTAROTATION, penultimate carbon, glycosidic bonds, hemiacetals, hemiketals, HAWORTH projection, and Fischer projections. Okay, so I don't know, you guys studied Fischer projection in organic chemistry, and we will be doing it here. So if you've not even studied Fischer projection in organic chemistry, we are going to learn it over here, so you'll be able to get it very well. Okay, so let's start with Fischer and HAWORTH projection. Okay, so a Fischer projection is just a representation of a sugar in their open chain form. Okay, so when you have a sugar molecule, in the representation of this sugar molecule in their open chain form is what we call a Fischer projection. Okay, so for a sugar, we have 6 carbons. So we have the first carbon here, the second carbon, the third carbon, the fourth carbon, the fifth carbon, and the sixth carbon. Okay, so these carbons are arranged in their open chain form. Okay, and this is called a Fischer projection. So this is how a Fischer projection looks like. Okay, and remember, we talked about chiral centers and chiral molecules in our last video, as I was saying. So in this compound, we can determine some chiral centers here, we can see that the carbon 2 is a chiral center. We can also see that carbon 5 is a chiral center, and carbon 4 is a chiral center, and carbon 3 is also a chiral center. Okay, so that's chiral centers for you. And if you don't know how to determine chiral centers, as I said earlier, you can go into the description and learn how to identify chiral centers. Okay, all right, so this is a Fisher projection for you, and this is a HAWORTH projection. Okay, so HAWORTH projection are often used to depict sugars in their cyclic forms. Okay, so as we have this sugar here, this is called glucose, D-glucose. Okay, D-glucose, and in no time you will learn why this is called a D-glucose and L-glucose. So we have enantiomers. All right, yes. So as I said earlier, carbohydrates, we need to know enantiomers, we need to do diastereomers and meso compounds. Okay, so we have enantiomers of glucose. So the first one is D-glucose, and we have L-glucose. So we will study them later and you get to know them. All right, so this is a cyclic form of a sugar, and it is called a HAWORTH projection. Okay, so these 6 carbons are represented in a cyclic ring. All right, so as you can see, we have carbon 1 here, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. All right, and we have this bond over here. Okay, so we will talk about this also in the meantime. This is a linkage. Okay, so it's a linkage, and we will determine how this linkage is formed over here. So it's between the penultimate carbon and the functional group of the other glucose. So that's how it will be forming. All right, so we have this functional group here, aldehyde functional group, and we have an OH here. So there is going to be a bond linkage between these two groups to form this linkage over here. All right, so we'll talk about it in the next slide. Okay, so our next terminology here is anomers. All right, anomer. So when we talk about anomers, they are diastereomers of cyclic forms of sugar or similar molecules differing in configuration at the anomeric carbon. That's carbon 1 of a sugar, an aldose sugar, or carbon 2 of a 2-ketose. All right, a ketose sugar. Okay, so when we talk about anomer in the simplest form, we have an alpha anomer and we have a beta anomer. So the cyclic form of carbohydrates can exist in 2 forms. So we have the alpha form and the beta form. Okay, and these are based on the position of the substituent at the anomeric center. Okay, so when we talk about the anomeric carbon is the carbon 1. All right, a carbon 1 of any sugar represented in the HAWORTH projection. Okay, so this is the Fisher projection and this is the HAWORTH projection. So carbon 1 here is called an anomeric carbon. Okay, so it's called an anomeric carbon, and this is also called anomeric carbon. And why do we have alpha D-glucose and beta D-glucose? So it's due to the position of the hydroxy group, the OH group at the anomeric carbon. So the position where it shows the direction determines either it's alpha or it's beta. Okay, so when the hydroxy group is in opposite direction to this functional group over here, the CH2OH, okay, that's the ethoxy group. All right, then we have an alpha D glucose. Okay, and we have an alpha D. Okay, so when we have the hydroxy group in the same direction as the carbon 6 over here, then they are in the same direction, and therefore we have a beta glucose. Okay, so that's the anomers for you, and the representation of a sugar in cyclic form. So these anomers can only be determined when sugars are in their cyclic forms. All right, they cannot be determined in their facial projection. We can't deduce whether this glucose is in the alpha form or a beta form. All right, since it's in the facial projection. So unless we convert it into a HAWORTH projection, all right, and in order to convert this into HAWORTH projection, there is a reaction, okay, between the functional group, aldehyde functional group here, and the OH here. Okay, so there is a loss of water between these two molecules. So there is H2O. So we have two hydrogens here and we have two oxygens here. So when there is H2O, that means two hydrogens are lost and one oxygen remains. So this is the one oxygen that is remain, and it forms a bond that joins carbon 5 and carbon 1 together. So there comes, we have an anomer. All right, so these are the basic terminologies, and this is anomer for you. Okay, so our next term is EPIMERS. Okay, so when we talk about an epimer, when sugars differ from one another in configuration at only one chiral center, they are called EPIMERS. So for instance, let's say we have galactose here and we have glucose. All right, we have D-glucose here, we have D-galactose, D-galactose and D-glucose. All right, so for example, glucose and mannose are epimers at carbon 2. Similarly, glucose and galactose are epimers of carbon 4. So let's consider these sugar molecules. So we have D-galactose here and we have D-glucose here. So the basic definition of an epimer is that the two sugars should differ at one chiral center. Okay, only one chiral center. Only one chiral center. So let's check galactose. When we check at carbon 1, we have a double bond then to oxygen here. We have a hydrogen here. We have a double bond to oxygen. That's the functional group of an aldehyde. Okay. When we come to carbon 2, we have hydrogen here, OH here. We have a hydrogen here, OH here. So they are the same. They are the same positions. Okay. When we come to carbon 3, we have HO here, HO here, hydrogen, hydrogen. So it's the same direction. So when we come to carbon 4, we have hydroxy group here. We have hydrogen here. So there were supposed to be hydroxy group and the hydrogen over here. But in this case, the position has been interchanged. So the chiral centers has been changed. Okay. So has been a change in their configuration. So it can be either R or S. So the change in sugars at only one chiral center is called an epimer. So when we take galactose and D-glucose, they are epimers at carbon 4. Okay, so it can come in your exams and they'll ask you determine which of the following sugars are epimers. All right, anomers and all stuff. So what you have to do is that in order to determine whether two sugar molecules are epimers, they are supposed to differ at one chiral center. So considering D-galactose and D-glucose, we can see here that they change in position. All right, so there is a change in position between this hydroxy group and hydrogen. Okay, so we have hydrogen here, we have hydroxy group here. So they have been swapped. So they can be termed as what? An epimers. So now let's compare D-glucose and D-mannose. We can also see that at carbon 2, there is a change in position between hydroxy group, which were supposed to be here, to here. So it can also be termed as what? An epimer. Okay, so that's the basic definition of an epimer. Okay, so let's continue with penultimate carbon. So when we talk about the word penultimate, it means last but one, or second to last carbon. So last but one or second to last. Okay, so the penultimate carbon in a sugar molecule represented in a facial projection is the last chiral carbon of the chain. Okay, so when you check D-glucose over here, we have carbon 1, 2, 3, 4, 5, 6. So the penultimate carbon is carbon 5. That's the last but one carbon, all right, and it's the last chiral carbon in the glucose molecule. Okay, so the alcohol group attached to this carbon is that which attacks the carbonyl group during cyclization of sugar. So as I said earlier, this is the cyclization reaction, and this leads to the formation of a HAWORTH projection. Okay, so in order to convert Fischer projection to a HAWORTH projection, there has to be a cyclization reaction, and this cyclization reaction is a reaction between the OH group at the penultimate carbon and the functional group of the aldehyde. Okay, so that there will be a loss of water in order to form that a bond between the glucose. Okay, so there is supposed to be a loss of water in order to form the cyclic sugar. All right, so this is the penultimate carbon at carbon 5 for D-glucose and the penultimate carbon for L-glucose. Okay, so this glucose, the L-glucose and the D-glucose, is just an enantiomer. All right, so when we talk about an enantiomer, it's just the mirror image. So it's the mirror image of each other. So when we check, we have OH here, OH here, OH here, OH here, hydrogen, hydrogen, OH, OH. So it's a mirror image of each other. So it can be termed as an enantiomer. All right, so that's the basic term for penultimate carbon. So that's what it means. It's a last but one carbon, or the fifth carbon in a sugar molecule, that is represented in a Fischer projection, to be precise. Okay, sure. Okay, so we are going to talk about glycosidic bond. Okay, so what is a glycosidic bond? So a glycosidic bond, or a glycosidic linkage, is a type of a covalent bond that joins carbohydrates or a sugar molecules to another group. Okay, which may or may not be another carbohydrate. So it can be the same carbohydrate. It can be a glucose, a glucose galactose, a glucose mannose, a glucose ribose, or a glucose galactose. All right, so it can be any sugar molecule. So a glycosidic bond is a type of bond, a covalent bond, that is formed between two sugars. Okay, so this is a glycosidic bond between two alpha D glucose. Okay, so a glucose and a glucose is called maltose. All right, so we have an alpha D glucose over here, and the reason why it is alpha is that it's opposite to the group, the carbon 6 over here. All right, so it's opposite in direction, and this is in the same, this is also in opposite direction, so they are all alpha groups. All right, sure, so they can be termed as alpha D glucose, and this is the glycosidic bond. So it's a bond, a covalent bond between two sugar molecules, and it is formed by the hydroxy group. So the two hydroxy group will also form a bond, and there will be a loss of water, there will be a loss of H2, so it will form this glycosidic bond. All right, and this glycosidic bond is a covalent bond. So for example, let's also consider lactose over here. So when we talk about lactose, we have a galactose and a glucose that forms lactose. So we have beta D galactose, and the reason why it is beta is that it is in the same direction, the hydroxy group is in the same direction as the carbon 6 over here. And the reason why it is a D glucose is that it's the first the enantiomer of lactose, and it's in the D direction, that's the right direction. Okay, so when you convert this cyclic sugar into a Fischer projection, you see that this is in the right direction. That's why it is a beta D galactose. Okay, and this is the glycosidic bond. Okay, so it's a bond between two sugars, which leads to a loss of water between the sugar molecules, and it forms a glycosidic bond. All right, Sure. So that's glycosidic bond. It's a bond between two sugar molecules. So as you can see here, we have a glucose sugar here and another glucose here. So the definition says which may or may not be another carbohydrate. So it can be the same carbohydrate or it can be another sugar molecule. Okay, so that's glycosidic bond. Okay, so another terminology that we need to pay attention to is mutarotation. Okay, so when we talk about mutarotation, we have to make reference to specific rotation. So it's an optical rotation, and we covered that in the third lecture. So you can go back if you haven't read it yet, so that you can know it very well. All right. So when we talk about mutarotation, it is the change in optical rotation due to change in the equilibrium between two anomers. Okay, so we have alpha anomer, beta anomer, as I said earlier in the previous slide. So when you check this molecule, it's in the same direction as the carbon 6. Okay, so it's a beta D glucopyranose. Okay, so this is a pyranose. Okay, yes. So an equilibrium reaction between this beta molecule can convert this molecule to an alpha D glucopyranose, and this is called a mutarotation. So it is the interconvertibility between two anomeric forms. So we can convert a beta D glucopyranose to an alpha D glucopyranose, and this is called a mutarotation. So cyclic sugars show mutarotation as alpha and beta anomeric forms interconvert. So when we change a beta D glucose to when we mutarotate it, that means we are changing the beta D glucopyranose to an alpha D glucopyranose. Okay, yes. So that's the basic terminology of mutarotation. So we are mutarotating it. So we are changing the configuration. So where we are changing the anomeric form. So if it's in the beta anomer form, then we are converting it to what? An alpha anomer form. Okay. All right. So another word that we have to know before we can study carbohydrates without any difficulties is ketal, acetal, and hemiacetal, and we also have ketal and hemiketal links. Okay. So hemiacetal or a hemiacetal is a compound that results from an addition of an alcohol to an aldehyde. Okay, so when we add an alcohol to an aldehyde, that means we are breaking the alcohol, the carbonyl functional group over here, and we are adding an OH group to this aldehyde. Okay, so we are adding an OH. Okay, OR, that's the alkyl group, to this form. All right. So when we add the OH, the hydroxy group, to this form, we are going to form a hemiacetal. So in short, it contains one hydroxy group bonded to the central atom. So we have one OH group bonded to a central atom. So it's a tetrahedral carbon. A tetrahedral carbon means it's having 4 bonds. Okay, so we have the one bond here, which is the R. We have a hydrogen bond here. We have an alkoxy bond here, and we have a hydroxy bond here. Okay, so it's a tetrahedral carbon. So a tetrahedral carbon with one hydroxy group is a hemiacetal. Okay, so we use it in the study of carbohydrates. Okay, so it's very, very important that you need to pay attention to. Sure, so that maybe you will not be confused when you meet these terms. Okay, and this also can be converted to an acetal by adding another OH group. Okay, so when we add this ROH, then we are converting this acetal to acetal, this hemiacetal to acetal. That means we are removing the OH group and we are adding R group, okay, to it, and it will convert the hemi to acetal. And in the acetal is also a tetrahedral carbon, but there is no hydroxy group. There is no hydroxy group. It's only alkoxy groups. Okay, alkoxy groups is a methoxy group. That's it's methanol. Okay, so it's a methanol. Okay, so it's an alkoxy group. So the acetals are tetrahedral compounds where two alkoxy groups, so OR groups, are bonded to the central atom. So in order to differentiate hemiacetal from acetal group, so for the hemiacetal we have one OH group and one alkoxy group, so one hydroxy group and one alkoxy group. But for acetal we have two alkoxy groups with no hydroxy group. So that's the difference between a hemiacetal and a hemiacetal and an acetal bonds. All right. Okay. So we are going to talk about a hemiketal and a ketal. So as we said earlier in the hemiacetal and acetal, we are also going to talk about hemiketals and ketals. So the hemiacetal is for aldehydes. Okay. So in order to convert aldehydes to acetals, that means we are using an aldehyde. Okay, so in order to get hemiacetal groups or acetal groups, we have to use aldehyde. And in order to get a ketal group or a hemiketal group, we have to use a ketone. So when we convert a ketone, okay, to a hydroxy, we add one hydroxy group to a ketone functional groups, we convert it to a hemiketal group. So a hemiketal is a compound that results from the addition of an alcohol to a ketone. All right, so when we add this alcohol to this ketone, we are adding one OH group to the ketone functional group. So we are going to get a hemi. A hemi means it's just half, so we are adding only one hydroxy group to this ketone, so we get hemiketal, as in the case of aldehyde. So when we add one hydroxy group to an aldehyde, we get hemiacetal, which is acetaldehyde, so it's an aldehyde. So in case of ketone, we get hemiketal for the first reaction. Okay, and in the acetal, the ketal, we have a functional group derived from the ketone by just replacing the carbonyl functional group by two alkoxy groups. So we add two alkoxy groups, so two RO groups, that's OR groups, to this ketone. So with that case, we are converting the OH over here also to OR groups. So it's the same as converting the aldehyde to an acetal. It's the same way as also converting a ketone into a ketal. Okay, so ketal and acetals have the same reactions. Okay, so it's just addition of two alkoxy groups to a ketone to get a ketal group and an aldehyde to get acetal groups. Okay, so that's these definitions that you have to pay attention to. Okay, so it's very, very important before we can study carbohydrates. You have to know these very basic definitions, which anomers, we have EPIMERS, we have MUTAROTATION, we have hemiketal, ketals, and EPIMERS. You have to know all these definitions. And don't forget about enantiomers, diastereomers, meso compounds. Okay, so because they are all going to help you to identify whether a specific sugar molecule is an enantiomer of the other, is an epimer, is an anomer, or any other molecule. And also don't forget the glycosidic bonds, how to convert a Fisher projection also to a HAWORTH projection. All right, so this is the end of the fourth lesson. And the fifth lesson, we are going to talk about carbohydrates into detail. So we are going to apply these basic definitions. All right, so these basic definitions are going to help us to study carbohydrates without finding any difficulties. Okay, so if you don't understand the enantiomers, diastereomers, stereoisomers, and the meso compound, just go back to our third lesson, or you can find it in the description so that you'll be able to guide yourself through the course. Okay, so we are just following it in order as a structure and function of biomolecules course. All right, so have a nice day and try to solve many questions on this so that you won't find many difficulties. You can find molecules and try to identify the chiral centers, try to identify whether they are ketals, try to identify whether they are HEMIACETALs, try to identify whether two sugar molecules are epimers of one another, they are anomers of one another, or others. All right, so try these basic terminologies and make sure you understand them very well before we study carbohydrates. All right, and don't forget to subscribe to this channel or like and make comments. So if you have any question, you can just go to the comment section and you can type it over there, and we will reply you as soon as possible to prevent any difficulties. All right, so have a nice day and hit the subscribe button over here for us so that you get notified when any video comes. All right, thank you very much.